Today, we're diving into a mathematical detective story. It's a quest that took 100 years, all to figure out the fundamental shape of our universe. And it all comes down to one, believe it or not, pretty simple-sounding question. And this is it. This is the Poincaré Conjecture. Just think about it for a second. Imagine you're in a space that's finite, but it has no edge, no boundary. If you could fly a spaceship in any direction and you never ever find a hole, does that automatically mean they're living inside some kind of giant three-dimensional sphere? For a whole century, that question totally stumped the smartest people on the planet. And yeah, this wasn't just some dusty academic puzzle. It was considered so important, so fundamental, that it was named one of the 7 Millennium Prize problems. And that came with a cool $1 million prize for whoever could solve it. You know, in the world of pure mathematics, the stakes really don't get any higher than that.
So the whole journey kicked off way back in 1904 with Henry Poincaré. Decades went by. Then in 1982, a mathematician named Richard Hamilton came up with a powerful new approach. But it took until 2003 for a reclusive genius, Grigori Perelman, to quietly post the papers online that would finally crack the case.
Okay, so what in the world does a mathematician even mean by no holes? Well, the fancy term is simply connected, but the best way to get a feel for it is with something you've probably got lying around. A rubber band.
This right here is the core idea. A space is simply connected if you can imagine taking any loop inside of it, like a lasso you've thrown, and you can always shrink it down to a tiny point without it getting snagged on anything. This really shows it perfectly, just in 2D. On a sphere, right? Any rubber band you put on it can just slide right off and shrink to nothing. But on a donut, if you loop that rubber band through the center hole, it's trapped. It's stuck. It can never shrink down to a point. That hole is a basic, unchangeable feature. So the Poincaré conjecture just asks, does that same logic hold true for a 3D space? If you can't find any of those traps loops, is the space guaranteed to be a 3D space?
For decades, nobody had a clue how to prove this. Then the breakthrough came from a totally different field, an idea that basically treats the geometry of space like temperature, and then tries to make it all even.
This analogy is absolutely key. Richard Hamilton's idea, called Ricci flow, is this incredibly powerful equation that works just like the heat equation does for temperature. You know how heat always flows from hot spots to cold spots until everything is the same temperature? Well, Ricci flow does the same thing for geometry. It smooths out all the lumps and bumps, evening out the curvature over time. The hope, the dream, was just beautiful in its simplicity. You could take any bizarre, lumpy, but still hole-free 3D shape, turn on the Ricci flow, and just watch it morph. The bumps would flatten out, the dents would pop up, and eventually it would settle into its most basic, fundamental shape, which, everyone hoped, would be a perfect sphere.
But there was a huge problem. As the flow was running, sometimes these infinitely dense spikes or super thin necks would start to form. They're called singularities. And they would basically break the math, threatening to rip the shape apart and just stop the whole process dead in its tracks. For 20 years, this problem seemed impossible to solve. And this is where Grigori Perelman enters the picture. He didn't just figure out a way around the singularity problem, he actually turned the problem into the solution, using a method we now call Ricci flow with surgery. Perelman's genius was to approach this like a surgeon. You start the flow, let the shape start smoothing out, and you watch for a dangerous neck pinch to form. Then, just before it can break, you hit pause. You carefully snip it out, patch up the new ends with perfect little spherical caps, and then you just press play again to continue the smoothing. You just keep doing that until no more of these singularities can possibly form.
His incredible proof really came down to 3 major breakthroughs. First, he came up with a formula that basically guaranteed the flow was always making progress, always getting simpler. Second, he figured out and classified every single possible type of singularity that could form. He showed they were predictable. And third, he created the strict, rigorous rules for how to perform that surgery perfectly every single time. Okay, so how does all this cosmic surgery finally prove the conjecture? This is the part where everything just clicks beautifully into place. Here it is. This is the crucial insight. Because you started with a hole-free space, a simply connected one, the surgery process itself can't create any new, fundamental holes. What Perelman proved is that any piece you snip off and any final shapes that are left over have to eventually become simple spheres. The result is just completely definitive.
As this chart shows, every single time you run the process on a simply connected shape, one with no holes, the flow and surgery method always 100% of the time ends with a collection of 3 spheres. But if you start with something that isn't simply connected, like a 3D donut, it will never become a sphere. The starting condition determines the final result.
And this leads to a really profound conclusion, which mathematicians sum up with this phrase: geometry forces topology. In this case, it means the topology, the simple fact that the shape has no holes to begin with, forces the geometry, that whole smoothing and surgery process, to arrive at one and only one possible destination, a sphere.
So, to put it all together, the Poincaré conjecture is true. Any closed, simply connected, three-dimensional space is really, deep down, a three-sphere. It might be all lumpy and twisted and distorted, but that's just a disguise. And Perelman's Ricci flow with surgery is the powerful tool that just systematically strips away that disguise, revealing the perfect shape hidden underneath.
And what about the guy who solved it all? Well, in a story that's become almost as famous as the proof itself, Grigori Perelman didn't submit his work to a fancy journal. He just posted it online for everyone to see. He then turned down the Fields Medal, which is basically the Nobel Prize of mathematics, and he turned down the $1 million prize. He said his contribution wasn't any greater than Hamilton's. And then he just retreated from public life entirely.
And that leaves us with this final thought. The Poincaré conjecture started as a question about a static shape, but the solution was all about dynamics, about a process of flowing and changing. It really makes you wonder, doesn't it? What other deep truths about our universe are just hiding out there, waiting not for a bigger telescope, but just for the right imaginative new tool to come along and reveal them?